Right, it's time to pick up the story with a new topic. I hope you're well rested because this is a vexing topic. It vexes me and it vexes many people within cognitive science, and it has done for a long time. It's a notion of representation by which we're going to ask, how is your knowledge about the world organized? When we started trying to say what cognitive science is about, one thing I suggested was it was about practical epistemology, about studying the relationship between the knower and the known from a scientific point of view. And that comes with challenges. We've met Descartes before, hiding away in the dark with his fingers in his ears, shutting himself off from the world and introspecting and convincing himself that he exists. Now, Descartes came up with the idea that mind and world were completely separate things. A metaphysical position nobody is happy with, nobody subscribes to. And yet our language is such that we often find ourselves talking as if the world and the mind were completely separate. And this is some version of separation of mind and world seems to underlie an awful lot of work done in classical psychology, in cognitive psychology in particular. Now, if we insist that mind and world are separate, then we have to sort of allow them to interact with each other. We have to provide some kind of story about how the mind comes to know the world. And most of those stories will involve some notion of representation. It's a vexed topic because an awful lot of the discussion, well, certainly from about 1960 to about 2000 in cognitive science, revolved around the notion of representation. Recall that around the middle of the 20th century, we had this change in vocabulary where the language of information processing started to be used. The activity of the brain was interpreted as being the same thing as mind, whatever that means. And with that, a lot of metaphysical problems were thrown up, which haven't gone away. But this notion of representation is not a simple notion. It unpacks into a variety of notions, and in this lecture and the next, we're going to undo a lot of that unpacking. And in order to warm up, we're going to simplify things, and we're going to stop talking about minds and worlds and all this crap just for a little bit, and we're going to talk instead about maps. I hope you're all familiar with the notion of a map. So, there's Salt Lake City. It's in Utah. Anyone here from Salt Lake City? Never is anyone from Salt Lake City. Anyone here ever been to Salt Lake City? Gosh. Does anyone here actually believe Salt Lake City exists? You believe it? All right. Well, there's a picture of it, so photoshopped. Salt Lake City is quite clearly not here right now. And on the basis of this, we're forming an impression of what Salt Lake City is like. This is a picture. Pictures are complicated things. This is a very special kind of picture. It's called a map. And this is a map of Salt Lake City. And this particular map contains a lot of information. It contains little black dots, which are buildings, and red lines, which are roads, and squiggly brown lines, which indicate altitude. And there's a lot of information that's available about Salt Lake City from this map. And there's some information about Salt Lake City that's not available from this map. So no matter how hard you study this map, you will never find out what it smells like in Salt Lake City. No point in sniffing the map. That information is simply not there. There's no information about the sounds of Salt Lake City on this map. That's clear to everyone. Some information on this map is entirely explicit. The name of a mountain is given there. Brandon Peak or something it's called. You can also infer a lot of things. You could find your way around Salt Lake City on this map. And that's a property of this map of Salt Lake City. Here's another map of Salt Lake City. This shows the territory around Salt Lake City. And Salt Lake City itself, most of the information on the previous map has now been condensed into a star in a circle. It looks like this. That's kind of bizarre, isn't it? Because even though none of us, myself included, have ever been to Salt Lake City, we all are confident that Salt Lake City does not look like a star in a circle. So the use of this is an example of symbolization, where we're using an arbitrary sign to stand for something that's not present. And you guys, as humans, linguistically capable humans, modern 21st century people, are experts at symbols. You swim in symbols. We use them all the time in all walks of life. We don't even notice it. But the relationship of if the relationship of this star to those bundle of streets in the city, in the middle of the city of Salt Lake City, is arbitrary and conventional, I think we'll agree it is, not all information on this map is of the same nature. We could figure out the distance from the town up north, Ogdeu, to the town below, Salt Lake City. If we had a piece of string, we'd have to do a bit of work to figure it out, wouldn't we? We'd have to lay the piece of string down on the map, trace it, find out how long the piece of string going the road is, and then take that and hold it up against the scale, and we could figure out how far it is in real life from one place to another. So we have to do a bit of work, but that information is there in principle because there's a systematic relationship between many elements of this map and stuff that's going on the ground. I hope you're beginning to see that the way that a map is about somewhere is itself complicated. It's a good thing we stuck with maps. Here's a map of Salt Lake City. There's different kinds of information on this map to the previous two maps. There'll be some overlap and there'll be some differences. You see the lake, for one thing. You really notice the lake in the last ones. This one helpfully comes with a legend in which it explains a lot of the conventions that are used here in the map. As competent map users, you expect there to be a set of conventions. When there's a little picture of an airplane positioned on the map, that gives you an indication of the position of an airport in real life. So some information is perfectly explicit. The names of places, for example, the labels of roads. You can consider that to be fairly explicit, the use of an aeroplane to indicate the location of an airport. Some information is present, but hard to get at. It's not explicit, like figuring out the distance between two places. And some information about Salt Lake City is just not present. The smells, the sounds, for example, are not present. Good. We're beginning to make some distinctions about the ways that something can be about something else. Let's come back to those symbols. The airplane stands in a relationship to an airport. Although the airplane is like a little picture of something you would find in an airport, it doesn't actually look like an airport. So there's something arbitrary, something somewhat conventional, that links that symbol with the actual airport. What about the third one down there? What's that? Anyone recognize that symbol? Yeah, if you're driving your car and that light comes on the dashboard, you've got oil problems. Go get you some oil or your engine will freeze up. How many of you have driver's licenses? Number. Some of you would have even seen this light come on, and some of you actually know what it means. How many of you have ever used an oil can like that? Can you really? Wonderful, wonderful, wonderful. It's actually, though, a little bit of history because the oil does not come in cans like that anymore. Like when you click on that floppy disk icon, that means save. Nobody uses floppy disks anymore, but we've all learned, there's a little bit of frozen history there. We've all learned the arbitrary association of that symbol with some activity. What about the bottom one? What does that mean? Shorthand for forbidden. It's a prohibition sign. It doesn't tell you what's forbidden, actually, in this instance, so that's kind of half of a sign there. But it means don't do it, right? Whatever it is. And here's a Russian sign that says, don't prohibit. Prohibition, prohibiting. Prohibited. Okay. That doesn't look like prohibition. Right? I don't know what prohibition looks like. I couldn't imagine whether it means anything to say prohibition looks like one thing or another. So that use is purely conventional. It's established by patterns of use, sort of agreement, consensus among a community of sign users. And we swim in signs. We live in an ecology of signs all the time. If you're driving on the road, Suddenly, a red light means stop, and a green light means go, and an inverted triangle means yield way, and dotted lines mean you're allowed to cross them, and straight continuous lines means you're not allowed to cross them, and the whole landscape is populated with these signs whose meaning is established conventionally. It could have been different. We could have used a square instead of a triangle for yield. Traffic lights could have been different colors. So this is established by convention. Now look at these things. On the top, you see a record of a kiss. Okay, it's a kiss of a person against a piece of glass. It's not a great kiss, but it's a kiss. On the bottom, you see a record of someone's hand meeting a piece of clay. In each case, the event that gave rise to this trace, this imprint, is gone. We nevertheless can find out some things about that event. Put on your Sherlock Holmes hat, let's do some forensics. You can tell, for example, that person had fairly big fat lips. You all know there's lots of different kinds of lips in this world. You can tell that the person who made the imprint had 5 fingers still on their hand. Imagine that piece of clay were still soft. We could stretch it and compress it. And we could change the relative size of the thumb to the other fingers and make the thumb really big and the other fingers really small. And in doing so, we'd be removing some information about the original event. So if we stretched it and compressed it, you couldn't tell the relative sizes of the fingers. But there's some information that would be preserved nonetheless. The relative ordering of the fingers, the fact that the thumb is on the opposite side of the hands to the little finger, that's not going anywhere unless we chop the piece of clay up. So some information about the original event is captured. Some may be modified, changed, translated as it were. And some is absent. You cannot tell, for example, what color eyes the person doing the kissing had. You cannot tell whether the person whose hand this is was wearing nail polish or not. That information is not there in principle. So these, similar to what's the information on the map, these are about something that's not present, but they're about it in an importantly different way. From the source event to the imprint, we can recognize a translation. Something is transferred. The image of the hand is transferred to the clay. The lipstick is transferred to the glass. Some properties are preserved, so we can tell about the relative size of the lips, the presence of all 5 fingers. Some's lost, so we can no longer tell the color of the eyes or whether the person was wearing nail polish. And some is modified, so if we're not sure that the clay has been unmoved, we wouldn't be sure necessarily about the relative sizes of things. So we've seen a couple of ways that something can be about something. And I guess the first thing to learn is that being about something is not a simple thing. It's not one thing. These are about an absent event. This is about Salt Lake City. The information on the map is about the real world in various ways. Most of the work in cognitive science has ignored this imprint version, but we'll come back to it. We'll find the presence of something like imprints in brains. Where most of the attention of the cognitive psychologists in particular has been more with the role of arbitrary symbols in an economy or an ecology of signs within a system, in other words. And this is a systematic view of representation, which is at the heart of a lot of cognitive psychology. On that view, something represents something else if it stands in correspondence to that thing, and it plays a role within the system because of the relationship of correspondence. Let me give you a very clear example. The word horse stands in correspondence to an animal with 4 feet, that has hair, that eats grass. But the word horse bears no necessary relationship to that animal. The word horse does not have 4 legs. The word horse does not eat grass. The word horse could be substituted in a different system with a different word. So if I say cheval, if I'm speaking French, or Pferd, if I'm speaking German, I'm moving from one systematic set of symbols to another systematic set of symbols. So the word horse works because it plays a role within a system, in this case the English language system. The relationship between a representation or a symbol and its referent can be arbitrary or it can be non-arbitrary. That top one there stands for a ratio, the ratio of the diameter of a circle to its circumference. It does not look like a circle. It doesn't look like a ratio. It doesn't look like the number 3.1416 blah, 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 blah. It's a Greek letter. It was chosen by mathematicians completely arbitrarily to stand for this one quantity. And if you're literate, if you understand the system, you have no problem interpreting it. Down below we have two examples where we have a mixture of things. The ways that these signs are about, well, what are they about? In each case, they're saying no fishing. Fishing is prohibited. They both make use of the rather arbitrary red circle with the line through it that means prohibition. They've both chosen to depict fishing, one with a picture of a person fishing and the other with a picture of a fish. So there's no necessary connection between the pictorial representation and the activity of fishing. Multiple ways of choosing it is possible, but it's not quite as arbitrary as the red circle with the red line. These function within an ecology of signs telling you where you can go, what you can do, what you're allowed to do. Please don't walk in the grass. The emergency exit is over here. Turn left for the shop. Those kinds of signs. And we are quite comfortable in that system. We work with these kinds of signs all the time. Now, coming back to our maps. Some of the elements in the map stand in a completely arbitrary relationship to things on the ground. This star standing for Salt Lake City is the best example I have of a completely arbitrary relationship. The relationship between other elements of the map and stuff on the ground, like distances, is more complicated. And you have to work hard in order to get at any individual distance, but that information is there. So some of this aboutness speaks of arbitrariness and symbols and systems, and some of it speaks of more principled mappings, and some of it maybe speaks of imprints. We're going to start off with what is often taken to be a canonical or a very clear example of representation in the brain about the world that is not of the symbolic nature, is of the imprint-like nature. You remember, because I know you were all here, when we studied vision, and we noted that the eyes are in the front of the head, but then there's nerves leaving the eyes, and they follow a weird route along the base of the brain, and they plug in, as it were, to the back of the brain in the occipital lobe. Now we can follow those connections, and we can observe that two places on the retina that are close together will project to two places in primary visual cortex that are close together. And two places that are far apart will project to two places that are far apart. So those spatial relationships on the retina are preserved somewhat in the mapping. So this is more, I'm going to answer my own question here and say this is more like an imprint than it is like a symbol. There's a principled causal relationship between places on the retina and places in the visual cortex. Notice that what's going on in the retina is related to what's going on in the world, and we're not actually investigating that relationship today. That's not what we're doing. We're going to consider the relationship between the sensory surface, that's the retina, and the brain. The relationship between the sensory surface and the tomato that you're about to eat raises a different set of questions. We can take this relationship, let's take a monkey brain. There's a monkey brain down the bottom, and there's a monkey retina up top. Now these are both schematized. Let's look at the retina first. Somewhat simplified. But there's a black area, small black area in the middle, that's the fovea. That's where the resolution is sharpest, where we've got color vision, where cones are. And it's very small. And around it there's a gray area called the perifovea. That's a bit bigger, has slightly different properties. And around that there's an area called the periphery, which is white, and that's the biggest of all. Now if we follow the projections from those areas to the back of the monkey's brain, this here is a picture of the back of the monkey's brain, but it's been opened up. So what you have to do is you have to fold those together so that those two, these are all inside the brain. Fold those together so they come together and you've got an intact brain again. Now you can see spatial relations are preserved. Things that are beside each other on the retina map to places in the visual cortex that are beside each other. But look what happened to the relative sizes. The relative size of the foveal area in the visual cortex is much larger. It's the largest of the three. The perifovea is somewhat smaller and the periphery is smaller yet. Recall, if you will, that clay tablet that I banged my hand into. Remember I said we could stretch it so that the relative sizes got changed, so that the thumb becomes grotesquely enlarged compared with the little finger. But we don't change some information. We don't reverse the position of the thumb and the little finger. We can't do that without chopping. So we've got something very like an imprint here, complete with those transformations, compressions and elongations and enlargements. That's vision. That's the relationship between primary visual cortex and the retina. Now we're going to look at the relationship between the skin and primary somatosensory cortex. This is the part of the brain in which light touch is registered. Up there is a brain. The red area is primary motor cortex. I know you all know that intimately at this stage. Just behind it, the blue one is primary somatosensory cortex. That's where we map, we can follow from the receptors in the skin all the way up to the brain there. So we can map from individual specific places on the skin to specific places in that area. And here you can see a cross-section through the brain for one hemisphere, and you can see a grotesque kind of deformation of the body. Now you cannot map the three-dimensional surface of the body onto a two-dimensional sausage like this without doing some cuts and chops. So there are some cuts here. We can reassemble the person, but keeping those relative sizes intact, and this is what we get. This is the sensory homunculus. You can see this person has really big lips, really big mouth, really big hands. Now think about where you're most sensitive on your body. If you touch your lips, you're extremely sensitive on your lips. You're sensitive on your fingertips. Compare that with your heel or your elbow or your knee. You're really not very sensitive there, and it's got very small knees and elbows and heels. There's an interesting fact about brain organization that we're not going to pursue at this point, which is that this is beside primary motor cortex, where we can look at a similar deformation of the body, and what we find is almost exactly the same homunculus pops out. Because those areas where we're most sensitive are those areas that we move best, right? We use the mouth for speaking. We use the hands for all kinds of intricate stuff. So it's no accident that the motor cortex and the sensory cortex are similarly organized. But notice what we've got here. We've got something like an imprint again. We've got a relationship between the sensory surface on the skin and the organization on the brain, in which local spatial relations are preserved, but with a lot of stretching and compression, that kind of thing. So we've seen this in vision, and we've seen this for light touch. There's one other modality we get this in, and that's hearing. But here the story is a little bit different. This is a cat brain, which is why it doesn't look like a human brain. Nevertheless, what we're going to look at is primary auditory cortex. Now the sensory surface here is inside the ear. It's the basilar membrane, which is inside the cochlea, and it's a long structure in which an incoming sound is broken down into its component frequencies. When you hear a complex sound like "argh," there's low frequencies in there, middle frequencies, high frequencies. You can analyze that sound, break it down into constituent frequencies. This should be familiar to you from your stereo system, where you've got a bass control and a treble control, or if you've got a fancy boombox, you have a graphic equalizer where you can break it down into multiple channels, low frequency to high frequency. I hope that's familiar to you. Well, your ear is doing something similar, and when we follow the projections then from the parts of the basilar membrane which are responding to low frequencies and those which are responding to high frequencies, we can follow those projections to primary auditory cortex, which is in the temporal lobe of the brain, and we find them organized here in the cat brain from low frequency sensitivity on the right to high frequency sensitivity on the left. So this is a tonotopic map, where the frequency layout on the sensory surface is preserved with some compression and some stretching in the cortex. So these are all weird maps from a primary sensory surface to a primary sensory area in the cortex. We've got a somatotopic map from the skin to the somatosensory cortex. We've got a retinotopic map from the retina to the back of the brain, the visual cortex, and a tonotopic map from the basilar membrane in the ear to primary auditory cortex. In each case, we have the structure of the stimulus is preserved, but it's modified somewhat, topologically warped. Some bits are compressed, some bits are enlarged. We've got different sensitivity when we compare the lips to the heels. So we can see a basic principle at work here, and this works only for those three modalities. Don't think of this as a general structure of perception. This doesn't work for taste. This doesn't work for smell. Doesn't work for the vestibular sense. Doesn't work for proprioception. Doesn't work for kinesthesia. It works for vision, for light touch, and for hearing. Now, because we can trace these relationships from the sensory surface all the way to the brain, a lot of people have said, well, in that case, the activity in the brain is clearly about something in the world. Hold on. We're mapping from the sensory surface to the brain. We're not discussing the relationship from the sensory surface to the world. We're leaving out that half for today. These are, the cortical activity that we're seeing are about something, is about something. It's about something that's going on the sensory surface. So this is a kind of a relationship of aboutness, and some people have talked of these maps, and they are maps as representations. We've just seen that maps are not simple. We've gone from maps of Salt Lake City to maps within the brain, but similarly we can see there's a kind of a principled relationship, in this case, between activity on the sensory surface and activity in the brain. And we can identify and follow these translations that move from cause to effect, just as we can follow how that imprint and that kiss mark came about. Most work on representations in the field of cognitive psychology is not concerned with these imprints, as I'm calling them, with this principled relationship between sensory surface and cortical activity. Most work is concerned with the more abstract question of how do you know something about the world. And let's start with this thinking cat here who's thinking about a cheeseburger. Now, if this cat is thinking about a cheeseburger, and if it's true that this cat is thinking about a cheeseburger, and the cheeseburger is nowhere to be seen, there's no cheeseburger present, then one might suggest something about the thinking is in relationship to a cheeseburger that's not present. So we've got this aboutness that needs to be explained. Notice that the framing assumption here, the background assumption, is that whatever's going on in the brain is where to look for thinking. One could question that. But we won't question it for now. We're going to follow the line of cognitive psychology that suggests that what's going on in the brain is where thinking is going on, and that something there must bear some relationship to cheeseburger, and we have to ask, what's that relationship? It has a name, it's called intentionality. Now you think of the word intention as meaning purpose, but here intention is used in a different sense. It's used in the sense of aboutness. It's a technical use. You can say aboutness, I absolutely don't mind. The argument is that if the cat is, for the cat substitute you thinking about your lunch, if you're thinking about your lunch and your lunch is not physically present, some elements in your thought stand in some relationship to your lunch, they represent your lunch, and what's the nature of that representation? Would we expect, if we were to look and read your brain, if we could look at all those patterns of activity going on in there, will we find something that looks like a cheeseburger, that tastes like a cheeseburger, that smells like a cheeseburger, or would it have no properties of a cheeseburger, like this has no properties of Salt Lake City? Now we're into some really, really interesting questions. If thought is a matter of symbols, then symbols stand in a relatively arbitrary relationship to something else, and they work because they occur within a system. Let's enlarge the system of English text to include this picture of a cheeseburger, and there's some perfectly good sentences. I want a cheeseburger, cheeseburgers are tasty, yes, we have no cheeseburgers. I could have replaced this picture of a cheeseburger with the letters C-H-E-E-S-E, etc., and it would have worked just as well. So there's no necessary relationship between a linguistic symbol and the thing that it stands for. When we speak of linguistic representations, we're thinking of thoughts that you might have that are like sentences. We've used a word for those before, we've called them propositions. So these are propositional representations. And if thoughts are like sentences, then these propositional forms are like your thoughts. Here I've used the mathematical symbol pi, and I've rebranded it to mean the kind of pie that Cartman likes to eat. Pie. Right? I can do that because the relationship between symbol and reference is arbitrary. We've met this before. We've met the language of thought hypothesis before. But a lot of people in cognitive science were not happy with this. Yes, they say, okay, that's great. I can see how language gives you a certain ability to reason and think. And remember the sentence we had about robbing orchards. They say, but that does not capture my thoughts. A lot of my thoughts are different. And so people, one of the biggest debates that's gone on has gone on about people who believe that thoughts are like sentences, like language, in which the relationship is arbitrary, and people who believe that some thoughts are not of that nature. Now, even Jerry Fodor, who gave us the language of thought hypothesis, will concede that there's lots of elements to your thinking that are not language-like. So I want you all to do an exercise. We're going to probe your little minds today a lot. I want you all to picture a hippopotamus. That was hard, wasn't it? Here's mine. Hands up if your hippopotamus was blue. Hands up if you're sure your hippopotamus was not blue. Now, if you had just taught the sentence, the word hippopotamus is neither blue nor not blue, you were able to go back and answer an unexpected question. You have a memory of what you thought. Hands up whose hippopotamus was definitely not wearing Wellingtons. Cool. So you can go back and you can ask questions of it that you couldn't ask of a sentence. So we're into the business of mental imagery here. It's very interesting. How much of your thought is like pictures? I don't know. So let's ask ourselves, was your hippopotamus somewhere? Was your hippopotamus in a zoo, in a swamp, in your bathroom, in your bed? Whose hippopotamus was definitely somewhere rather than just in an abstract nowhere? Some of you. Okay. Were there any other elements in the picture you had of a hippopotamus? Were there trees and swamps, or was there another hippopotamus there? Who's sure there was something else there? Some of you. So you can go back and you can query this, just as you could query a photograph. You could go back to a photograph again and again, and as it were, notice things, or verify, establish that something is or is not the case by repeatedly going back to it. You can do that with an image, and you cannot do that with a sentence. So this introduces the great mental imagery debate. If thoughts are things that are about something in the world, they could be about them in a language-like way, and that would be a very arbitrary relationship that only supports some information and doesn't support others. They could be about them more like an image is about, where the relationship between the representation and the world is more lawful, more constrained. It's richer in some respects. Around this time, around the middle of the 20th century, when people started thinking of brains as computers, an optional view, I stress, when people started thinking of them as computers, then this became very, very important, because computers manipulate symbols. And mapping from that language onto natural language, onto human language, is fairly easy. Mapping it onto images is much more difficult. So here's the kind of experiments that was done to probe to see what role do image-like representations play in your thought. Are those two the same shape? Put your hand up when you're sure whether they are or are not the same shape. You got to kind of mentally rotate one onto the other. And if you do so, should come a point at which you say, is it the same or not? It is the same. Okay, if that was difficult, try this one. It's a little bit easier. Put your hand up when you're sure you can do it. You know the answer? It's not hard. Come on, put your hand up when you're sure you know the answer, whether these are the same shape. Some people are still unsure. What's the answer? Is it the same shape? I'm seeing more yeses. What about this one? Put your hand up when you're sure. And what's the answer? No. The answer is no. Okay? You can go back and revise the notes and you can check this for yourself, but the answer here is no. So, if when looking at these, you were creating a language-like representation of them, it's hard to understand why some of these tasks are easier than others. But when we run lots of subjects, here's the kind of data we find. On the bottom here, this is a simple two-dimensional rotation task. You can see from 0 to 180 degrees, that's the amount you would have to rotate to map one onto the other. On the y-axis here, you've got the response time. That's the amount of time people took to make up the decision. And you can see that there's basically a straight line relationship from 0 up to 180. Now, going down on the other side is just because you've just gone past the halfway mark and you're going back, aligning them. So it's from 0 to 180 is the interesting one. There's two lines there because people always take longer if they're not the same than they do if they're the same. You know, because you just want to check. Whereas when they're the same, there's this kind of satisfying mental click you get. Yes, I matched one onto the other. So what this shows is that given a task of this nature, where people are just thinking, it takes them longer if these were real-world objects, embodied objects out here in the real world, if the amount of rotation needed to map one onto the other is larger, it takes you longer to do this in an abstract thought sense as well. So whatever way you're representing these, whatever way your thoughts are organized, they have some space-like properties, some spatial properties, because it's taking you longer to mentally rotate, just as it would take you longer to physically rotate in space. These have been very influential, and what they show is that, well, we can think of some kinds of aspects of thought as being language-like, but we're not done. There's the possibility, at least, of image-like representations that have spatial properties, and we've already probed your hippopotamus image to verify that it has certain properties that are not language-like, that are more image-like. And the way that something is represented influences what you can do with it. If Salt Lake City is represented like this, it's not going to be much use for finding your way around addresses in Salt Lake City. Here's another example. You're all familiar with numbers. Well, we can represent the problem down there, the addition of 3,456 to 284. We can represent that, as in the bottom left there, using a decimal system of notation. Or we could represent it using Roman numerals down here. I'll guarantee you that the addition problem is an awful lot easier to solve if you represent it using the conventional Arabic numerals, with a place-based system of notation, all in base 10. Roman numerals use a bizarre conjunction of base 2 and base 5, lots of arbitrary conventions that make it great for carving these numbers into stone, but rotten for doing arithmetic. Right? You wouldn't know where to start doing arithmetic using Roman numerals. It's doable. It would be much easier to convert them into our kinds of numbers, add them, and then convert them back, than to do the arithmetic in Roman numerals. So although the two representations contain the same information, the way that it's represented influences what you can do with it. So now we're going to do some more mind probing. We're going to start not with minds, not with the organization of knowledge in your mind, but with the organization of knowledge in the world. I'm sure you're all familiar with the old notion of a phone book. Nobody uses them anymore, but it's a big-ass book you get delivered to your house, and it's got a list of everyone's got a phone, landline, and their phone number. Everyone's seen a phone book, I hope. If not, this is going to fall really flat. Okay, if I give you a phone book, and I tell you to look up the number of Mr. Thelonious Winterbottom, what are you going to do? You're going to take your phone book, you're going to go right to the back of it, you're going to go W, there we go, W, W, E, W, I, okay, W, I, and within about 10 seconds you'll be able to deliver me the number of Mr. Thelonious Winterbottom. I hope you're all confident that you could do this amazing feat with a phone book. Here's another problem. Given a phone book, who owns that number? You know what we're going to have to do, right? The numbers, the way a phone book is organized, they're organized by last name and not by number. So the information is in the phone book. There's no doubt about it. But the only way to get at it is to start at the first page and go through and look at each phone number and see, is it or is it not the number you're looking for? You'd probably kill yourself before you're done. It'd be a horrible task. And even when you got to the end, you missed it somewhere in the middle. It'll be ghastly. So the information is in there in principle, but in practice, the way that your knowledge is organized in a phone book makes answering the first question easy and makes answering the second question really difficult. So we can find out about the way the phone book is organized by seeing which questions are easy to answer and which questions are hard to answer. Now let's do some more stuff, but this time we're going to ask about the way that your knowledge is organized in your heads. I'm afraid I'm going to show my age here a little bit, but anyway. Name 3 bands who are a bit like Nirvana. Now really, I don't really care about the domain. I'm fairly confident that everybody would have not too much difficulty doing this. Pearl Jam, Soundgarden, I don't know. I don't really care whether you think those bands are or are not like Nirvana. It's the kind of question you can answer, right? The Beach Boys are a little bit like the Monkees or a little bit like the Beatles. It's not hard to come up with an answer to this question. Whether it's the right answer or not, who cares? Now, I know you know a lot of bands. Here's a different question about bands. Name 3 bands where the third letter in the band's name is U. The information's in there somewhere, but it's a bit like that phone book example, isn't it? Because it's hard to think of bands based on the third letter of their name. So you start off, you go, okay, Beatles, B-E-A, no. Okay, Led Zeppelin, L-E-D, no. Okay, anyone think of one that is? It's really, really hard, isn't it? Bruce Springsteen and the E Street Band, yeah. Soundgarden. There you go, I got one. But it's really, really hard because whatever you know, and you do know this, you know how the bands are spelled and so on, but that is not a good way. I mean, this information is not freely accessible. Whatever way your knowledge about bands is organized, it's not organized to facilitate this kind of question. So you can see that we can ask, by asking questions, we can find out some way, we can find out some things about how your knowledge is organized. Here's an example of a kind of question that phonologists have been known to ask. Name 3 words that rhyme with flap. Go.
Slap.
Clap. Slap. Tap. Tap. Okay, we got them. That was really, really easy. Map. Nobody said map after all my priming. Nobody said map. It was really, really easy, and phonologists have found lots of evidence that rhymes are really important to our knowledge of the sound structures of a language. Rhymes are important, and somehow our knowledge about English words are organized in ways that allow us to answer questions about rhymes really, really easy. So we've seen 5 examples here. 2 on the phone book, and here we know what way the information is organized in the phone book. We know that the way it's organized makes it easy to find a number given a name, but very hard to find a name given a number, even though the information is in there. Remember our maps, some of the information was hard to get at, some of it was explicit. So the way that knowledge is organized hugely affects what you can do with it, how you can access it. And those grand challenges 3 and 4, which were about bands, and 5, which is about rhymes, tell us something about how your knowledge of a given domain is organized. So even though these are difficult questions to answer, I think you can see that when we ask, there's some questions we can ask that can be really, really informative and can tell us, reveal to us about how our knowledge is organized, even though we don't know, for example, what the role of a brain is in all this. We can ask these questions and still be agnostic as to what that signifies, what we can conclude from that. Nevertheless, our knowledge is organized. It's organized in certain ways, and that greatly influences what we can do with it. Okay, we're going to stop there, and we're going to pick up the theme on Thursday.